the most surprising, most shocking, and most unsensible things about the universe that we've discovered in the last 100 years. One of the most profound discoveries in cosmology, and that is that empty space weighs something. That if you take all of the particles and all the radiation out of space, and all you have is empty space, that empty space weighs something. And that is crazy. That is insane. But it's true. And it's changed everything about the way we think about the universe, everything we think about everything, and everything we think about nothing. Because suddenly empty space has a characteristic that we never would have imagined. But the Higgs is another example of that, because the discovery of the Higgs is truly remarkable, because it validates another crazy notion that physicists have proposed 50 years ago, which I figured had to be wrong, because it just seemed too good to be true. It just seemed too slick. And that was that there's a background field permeating all of space right now, which is invisible. And elementary particles moving through space interact with that background and get resistance. They get slowed down. One of the great intellectual triumphs of the last part of the 20th century was the unification of two forces in nature. The last major unification happened with Maxwell and Faraday 100 years earlier, when electricity and magnetism, two very seemingly different things, were shown to be really different manifestations of the same thing. That's the characteristic of science. Science shows us, really, and we know we've made progress, when two very disparate, or more than two, when very disparate phenomena are understood as different manifestations of the same thing. That was what's so great in some sense about Darwin. The diversity of life could be understood not as special creation for every species, but by a simple principle of natural selection. And Maxwell and Faraday unified electricity and magnetism. And in the 1960s, there are these two forces in nature we knew about. There are four total. Electricity, and magnetism, which is responsible for everything we see, and almost all the things that govern the way we work. All of chemistry is basically electromagnetism. And the so-called weak force, which is really weak, and unlike electromagnetism, which is long range, you can feel static electricity far away, the weak force only operates on the size of a nucleus or smaller. And the weak force is responsible for the nuclear reactions that power the sun. These two forces seemed as different could be. But it was shown that they were different manifestations of the same force. They could be thought of that way, but only under one condition. See, the reason electromagnetism is long range, we now know by quantum mechanics, is because in quantum mechanics, in quantum field theory, all forces are mediated by particles, by the exchange of particles. And electromagnetism occurs because particles called photons are exchanged between objects. That's why you feel static electricity, and photons from that light are coming to my eyes and I can see. So photons are the mediator of electromagnetism, but they have zero mass. That's why they travel at the speed of light. Zero mass objects travel at the speed of light. But the mediators of the weak force were speculated to in fact weigh 100 times the mass of the proton, which is one of the reasons why the force was so weak and so short-ranged. In the 1980s, at CERN, in fact,
same
place, not quite the same machine, a much smaller machine, discovered the particles that mediate the weak force. So the whole theory seemed right, that the two forces could be different manifestations of the same thing. But how could they be? How could the mathematics produce a very massive field and a very massive field? Well, if the mathematics at a fundamental level predicted that everything was massless, then the two forces would look identical at some fundamental level. But how could you make one appear to be massive? Well, if there's a Higgs field, if there's a field which we now call the Higgs field, and the particles that mediate the weak force interact with that field, and as they move through space, they get resistance, just like a swimmer swimming through molasses. They'll act like they're heavy. And if the photon doesn't interact with that field, it'll remain massless. And so you could have the mathematics of the two forces look identical at a fundamental level, and it's just an accident of our existence because this Higgs field exists that the weak force becomes weak. And of course, physicists are like Hollywood. If it works, keep repeating it. And it was realized by Steve Weinberg, in particular, that in 1967, that, well, the same thing could apply to the rest of particles of nature. Particles could get mass because they interact with the Higgs field. Those that interact more strongly act heavier. Those who interact less strongly act weaker. And so everything the theory held true, except we never saw the Higgs field. And as I think I said in the New York Times piece, inventing invisible fields is the province of religion, not science. Science, you got to measure it. And the great thing about quantum physics is it tells you if you slap that field hard enough in a very small region with enough energy, you'll produce real particles. And so for 50 years we've been trying to build a machine that had enough energy in a small enough space where we could produce those real particles if they existed. And I was betting against it because almost all predictions are wrong in science. We're almost always wrong. If it weren't, anyone could do physics. And it just seemed too good to be true. And my first reaction when I heard that the Higgs was discovered was, it's too good to be true. But it's one of the rare cases, and I mean rare cases, in spite of what the popular media tells you about people like me sitting in a room, you know, at night writing equations down and discovering the universe. Almost always, experiment leads theory. And this was an example where theory led experiment. We were right, and it's amazing. But it reinforces the notion in this book, which is what I was just writing about for one of the pieces, because it tells us that empty space has this Higgs field. So empty space is far more complicated than you would ever imagine. In fact, quantum physics tells us that empty space is a boiling, bubbling brew of virtual particles that are popping in and out of existence all the time in a time scale so short you can't measure it. So nothing, and the nothing of the Bible, I would argue, is empty space. The nothing of the Bible is an eternal dark void. Okay? So that nothing, in fact, is quite full of stuff. That nothing is not what we thought it was. And in fact, as I show in the book, that kind of nothing is unstable. And if you wait long enough, it'll produce stuff. It's guaranteed to. So the really surprising thing would be not to ask why is there something rather than nothing, but why is there nothing rather than something? But no one would be around to ask that question if there were nothing. So it's not surprising at all. It's just kind of obvious. It's natural that there should be a universe full of stuff. Because empty space is unstable. And empty space and nothing are not what we thought it would be. Now, there are people with, and you see, this offends people, both philosophers and theologians, because especially the theologians would like to define nothing to be that from which only God could create something. And clearly, if empty space can create something, then it can't be nothing. And they would tell me that. And I'd say, okay, well, it turns out if you apply the laws of quantum mechanics to gravity, then even empty space itself becomes a quantum mechanical object, and spaces can be created from nothing. You could start it with no space, and you can create a universe by a quantum fluctuation. And under very particular conditions, it'll survive to be our universe. And the interesting thing is when we look out at our universe, and I spend about 150 of the pages and 200 pages in this book or so, showing it's amazing that when we look at the characteristics of our universe, they are just the characteristics that you would expect of a universe that was created from nothing. It didn't have to be that way. It could have worked out differently. Now, does that prove it came from nothing? No, but it's plausible. Everything we see is consistent with that, which is itself remarkable. And then the final thing that people would say is, well, you know, okay, you got no particles, now you got no space, but you got the laws of physics. Who created the laws? You need God for that. And as I argue, many of the ideas we're coming up in physics now suggest to us that even the laws of physics are accidental. They may have come into existence when our universe came into existence, and there are reasons for believing that. But the final part of nothing, and I want to do it in deference, we were talking about my good friend Christopher Hitchens, who was writing the foreword for this book before he died. And I was fortunate enough to speak at his memorial service recently. He was an amazing man. When I talked to him about this, and I talked to him about physics a lot, I told him that, you know, one of the consequences of a universe being dominated by nothing, right, empty space weighing stuff, is that the future is really miserable. That the universe is expanding faster and faster, and if we wait long enough, all the galaxies we now see will disappear. Everything we observe in the universe outside of our own galaxy will disappear. We won't see it, because it'll take about almost 1 trillion years for that to happen. But and there'll be stars around in 1 trillion years, and observers around those stars will look out, and they'll think they measured, they'll look at the universe, they'll think they live in the universe we thought we lived in 100 years ago. With a single galaxy that's static and eternal, because there'll be no evidence for the expansion of the universe, because there are no other galaxies to trace the expansion, and I discussed that. And so, and Christopher said to me, nothing is heading towards us as fast as can be. Because, of course, everything's going to disappear from the universe, then our stars are going to die out, and the universe become cold, dark, and empty. So the ultimate answer to the question, why is there something rather than nothing, is just wait, there won't be for long. And I like that answer because it points out the ultimate conceit that we have, that we are somehow the pinnacle of creation. That as far as evolution is concerned, it's stopped here. It was already just so we could be here. And of course that's garbage. Similarly, the idea that the universe was created so we could be here, or in some sense that the universe will remain the same, is ludicrous. In the far future it'll be quite different. We are lucky to be living here at this brief moment in cosmic history when we can see what we can see. And so, if we live in a purposeless universe, for which there's every bit of evidence, or to put it the other way around, there's no evidence of purpose in the universe. That doesn't mean there isn't, but there's no evidence of purpose. That shouldn't depress you. And if the future is miserable, it shouldn't depress you. Because we're so fortunate to be around right now when we can see all this stuff and figure it out and have evolved brains that can do this stuff, that we should realize that the meaning in our lives is the meaning we make. And science, in my opinion, provides much firmer, if you think about it, spiritual fulfillment by making us uncomfortable rather than comfortable.